All right, so let's jump into it. So 3.1, current. Okay, so current, just to state it right up front, is simply motion of charge. So we've been talking about stationary charges, but now we're going to talk about collective motions of charge. So if you consider a conductor, right, a material like a metal that's a good conductor of electricity, with nothing else attached to it, right? Then the atoms that make up the metal have associated conduction electrons that are able to freely move within the material. These are the free electrons that move about, and they move at random in all directions with no organization, right? So you might have one electron moving this way, another electron moving that way, another one moving this way. I guess these would all get a minus sign. So they're moving a lot, but kind of like molecules in a gas, right? But they're moving even faster, so 10 to the 6th meters per second. But the net motion of charge, right? If you were to, the collective net motion, if you were to sum all of this up, there's no net motion of charge, 0 meters per second. For every moving charge that's moving one way, there's another that's moving the other way, that if you sum it all up, it all kind of cancels out. It's just movement at random, right? But now let's consider that same material, but we set up a electric field inside. So let's say we have this conductor here, like this cylinder or whatever. You can think of this as a wire, I guess, since that's what we're building up towards. Let's say there's an electric field, which I guess I've been using as green, going in this direction, right? And let's say we have a negative charge here. Well, it's going to experience a force equal to its magnitude of charge times that electric field. And that force is going to be this way, since it's negative and the field is pointing to the left, so it's going to be motivated to move to the right, yeah? And that's how every charge, if we're talking about electrons, which are the things that are moving in the metal, that's how every charge is motivated to move. And so since all the electrons are moving in the same direction, then you have some net charge to the right, some net current to the right. But if we look at what's going on the inside, an electron's path is oftentimes obstructed by lots of things. It collides with relatively large ions, right? The atoms and the nuclei in its path that make up the material itself. So despite these collisions, there's still a net velocity of electrons to the right, but it's slower than than you might think, right? It's slower than if their path were unobstructed. If they were unobstructed, they didn't collide with anything, then this electric field would continue accelerating them faster and faster and faster off to infinity if your wire was infinitely long, I suppose. But that's not really what happens. They are slowed down to this certain velocity called the drift velocity, based on the amount of collisions that they experience in the material. And so drift velocity, here, drift velocity, V sub d is usually what it's denoted as, is the velocity that the electrons actually move, and it's much slower than you might think, right? It's not the speed of light. Even though you flip on a switch and then the light comes on instantly, the electrons that were at the light switch that you flipped with your hand did not travel in that time all the way over to the light. Their drift velocity is relatively slow, which is kind of interesting. So we define current in kind of a stupid way, I'll say, considering that it's really the electrons, the negatively charged electrons that are moving. Despite this, we define current according to the convention of the direction of flow of the positive charge. Historical reasons, I guess. We know that it's really the negative charges that are moving. It's the electrons that are moving about the circuit, because those are the things that are free to move within an atom in a conductor. But that's the convention to describe current, right? So mathematically, we would write current, which is denoted with an I, not necessarily cursive, delta Q per delta T. So how much charge flows past a point in time t? Notice that current isn't a vector, right? I deliberately did not write it as a vector. Charge isn't a vector, and time isn't a vector, so it's not a vector. This is because a current-carrying wire, you can bend it and move it, and the current is always along the length of the wire. So if the wire is bent, the current still follows along the length of the wire, and we don't need to care about describing its direction in XYZ space. It's just along the direction of the wire. That being said, we do oftentimes describe the direction of current in a circuit overall as, like clockwise around a circuit, right? So if you have a circuit like this, just a wire and a loop, and you have, certain components on the circuit, you might say that the current is going in this counterclockwise way or clockwise way, right? So that's about as far as we go for direction of current. So lastly, the SI unit of current is the ampere. So ampere or amp, right? So if you heard somebody say 30 amps, which is actually a lot, they're talking about units of current, capital A. And the units that breaks down to is coulombs per second, which makes sense, right? Charge per time.